In probability theory and statistics, the beta distribution is a family of continuous probability distributions defined on the interval 0, 1, parametrized by two positive shape parameters, denoted by alpha and beta, that appear as exponents of the random variable and control the shape of the distribution. The beta distribution has been applied to model the behavior of random variables limited to intervals of finite length in a wide variety of disciplines. For example, it has been used as a statistical description of allele frequencies in population genetics, time allocation in project management, control systems, sunshine data, variability of soil properties, proportions of the minerals in rocks in stratigraphy, and heterogeneity in the probability of HIV transmission. In Bayesian inference, the beta distribution is the conjugate prior probability distribution for the Bernoulli binomial, negative binomial and geometric distributions. For example, the beta distribution can be used in Bayesian analysis to describe initial knowledge concerning probability of success, such as the probability that a space vehicle will successfully complete a specified mission. The beta distribution is a suitable model for the random behavior of percentages and proportions. The usual formulation of the beta distribution is also known as the beta distribution of the first kind, whereas beta distribution of the second kind is an alternative name for the beta prime distribution. History. The first systematic modern discussion of the beta distribution is probably due to Carl Pearson, FRS, an influential English mathematician who has been credited with establishing the discipline of mathematical statistics. In Pearson's papers, the beta distribution is couched as a solution of a differential equation, Pearson's type 1 distribution, which it is essentially identical to except for arbitrary shifting and rescaling. In fact, in several English books and journal articles in the few decades prior to World War II, it was common to refer to the beta distribution as Pearson's type 1 distribution. William P. Elderton, in his 1906 monograph Frequency Curves and Correlation, further analyzes the beta distribution as Pearson's type 1 distribution, including a full discussion of the method of moments for the four-parameter case, and diagrams of U-shaped, J-shaped, twisted J-shaped, cock-hat shapes, horizontal and angled straight-line cases. Elderton wrote, "I am chiefly indebted to Professor Pearson, but the indebtedness is of a kind for which it is impossible to offer formal thanks." Elderton, in his 1906 monograph, provides an impressive amount of information on the beta distribution, including equations for the origin of the distribution chosen to be the mode, as well as for other Pearson distributions. Types I through 7. Elderton also included a number of appendixes, including one appendix on the beta and gamma functions. In later editions, Elderton added equations for the origin of the distribution chosen to be the mean, and analysis of Pearson distributions 8 through 12. As remarked by Bowman and Shenton, Fisher and Pearson had a difference of opinion in the approach to estimation, in particular relating to moments and maximum likelihood in the case of the beta distribution. Also, according to Bowman and Shenton, the case of a type 1 model being the center of the controversy was pure serendipity. A more difficult model of four parameters would have been hard to find. Ronald Fisher was one of the giants of statistics in the first half of the 20th century, and his long-running public conflict with Carl Pearson can be followed in a number of articles in prestigious journals. For example, concerning the estimation of the four parameters for the beta distribution, and Fisher's criticism of Pearson's method of moments as being arbitrary. See Pearson's article, Method of Moments and Method of Maximum Likelihood, in which Pearson writes, "I read which, as far as I am aware, is the only case at present published of the application of Professor Fisher's method. To my astonishment, that method depends on first working out the constants of the frequency curve by the method of moments and then superposing on it by what Fisher terms the method of maximum likelihood, a further approximation to obtain what he holds. He will thus get more efficient values of the curve constants. David and Edwards's treatise on the history of statistics cites the first modern treatment of the beta distribution in 1911, using the beta designation that has become standard due to Corrado Gini, an Italian statistician, demographer, and sociologist, who developed the Gini coefficient. N.L. Johnson and S. Coates, in their comprehensive and very informative monograph on leading historical personalities in statistical sciences, credit Corrado Gini as an early Bayesian, who dealt with the problem of eliciting the parameters of an initial beta distribution by singling out techniques which anticipated the advent of the so-called empirical Bayes approach. Bayes, in a posthumous paper published in 1763 by Richard Price, obtained a beta distribution as the density of the probability of success in Bernoulli trials. But the paper does not analyze any of the moments of the beta distribution or discuss any of its properties. Characterization. Probability density function. The probability density function of the beta distribution, for 0x1, and shape parameters alpha, beta greater than 0, is a power function of the variable x and of its reflection as follows, where gamma is the gamma function. The beta function is a normalization constant to ensure that the total probability integrates to 1. In the above equations, x is a realization, an observed value that actually occurred, of a random process x. This definition includes both n's x equals 0 and x equals 1, which is consistent with definitions for other continuous distributions supported on a bounded interval, which are special cases of the beta distribution. For example, the arc-sine distribution, and consistent with several authors, like N. L. Johnson and S. Coates. However, several other authors, including W. Feller, choose to exclude the n's x equals 0 and x equals 1, and consider instead 0 less than x less than 1. Several authors, including N. L. Johnson and S. Coates, use the symbols p and q for the shape parameters of the beta distribution, reminiscent of the symbols traditionally used for the parameters of the Bernoulli distribution. Because the beta distribution approaches the Bernoulli distribution in the limit when both shape parameters alpha and beta approach the value of 0. In the following, a random variable x beta distributed with parameters alpha and beta will be denoted by other notations for beta distributed random variables used in the statistical literature and differential equation. The PDF of the beta distribution is a solution of the following differential equation, which follows from the slope of the probability density function. It follows that at 4, the slope of the density function is 0. Cumulative distribution function. The cumulative distribution function is where is the incomplete beta function and is the regularized incomplete beta function.